These are examples for section 13.5, trigonometry and area. We now have two ways to find the area of a triangle when the height is not given. Recall that we used Heron's formula when we basically had a side-side-side or SSS situation. We had all three side lengths, no angles, and no height. Before that, we learned how to find the area of a triangle when we're not given the height again, except this time we have an angle and the two sides on either side where the angle's included. We used trig to do this, and in the lesson, if you recall, we derived the formula, which is A equal 1/2 BC sine angle A. So, taking a look at this triangle, what is the area of the triangle at the right rounded to the nearest tenth? We've got an angle, and as long as we have the side lengths on either side of that angle, then we can use this formula. So, this will be my angle A, and it doesn't matter where B and C go, but since I put B here, lowercase b is 12, opposite angle B, and opposite angle C is lowercase c. So using these values, we have the measure of angle A is 48 degrees. We have B, the length is 12 centimeters, and the length of C is 21 centimeters. Using the formula, we have the area equals 1/2 times B, which is 12, times C, which is 21, times the sine of angle A, which is 48 degrees. We start to simplify it. Notice that 1/2 and 12 are divisible by 2. 2 goes into 2 once. 2 goes into 12 6 times. Now we have 6 times 21 sine 48 degrees. Now we can multiply the 6 and 21 and we get 126 sine 48 degrees, and that's in centimeters squared. They asked for the approximation, so we take our calculator. Make sure you're in the degree mode. In your calculator, and put in 126 times the sine of 48, round to the nearest tenth, and you get about 93.6 square centimeters. The area of this triangle is close to 93.5 square centimeters. Example 2. What is the area of a regular nonagon with 7 centimeter sides rounded to the nearest tenth? So here we have a nonagon, 9 sides, so n is 9. Previously, you've used a little bit of trigonometry to find the area of regular polygons. In this particular problem, however, we're given the length of a side, but we're not given the apothem length, and we're not given a radius length. Notice what happens. First of all, draw radii, at least 2 of them. I'm going to draw radii CP and CR and the apothem and call it A. So take your straight edge, draw radius CP, draw radius CR. Of course, you can draw more radii than this if you want or need to each vertex. And before we draw the apothem, let's find the central angle measure. Central angle measure is 360 degrees. Since we're going off the center, it's going to go all the way around 360 degrees, divided by the number of angles or sides, which is 9. So 360 degrees divided by 9, and we work that out, and we get 40 degrees. So the measure of a central angle here is 40 degrees. Immediately after that, we draw the apothem, or one of the apothems, between the 2 radii. Remember, the apothem, A, will bisect that side into 2 congruent parts. It's perpendicular to the opposite side, and it bisects the central angle into 2 congruent angles. So, the angle created by A The apothem is 40 divided by 2, which is 20. 20 degrees. So each one of these is 20 degrees. Coming down here, we have 20 degrees here. We have the apothem, and PR is the length of one side. It's 7 centimeters according to the problem. Since it cuts it up into two congruent parts, from here to here would be 3.5 or 7/2 centimeters. Now we have enough in this right triangle to use a trigonometric ratio. So we write the formula for the area of a regular polygon. A equals 1/2 AP, apothem, times perimeter. And starting with A, we determine which trig ratio to use. And since this is the angle, we're looking for the adjacent side, and we have the opposite side. So opposite over adjacent, using the TOA part of SOHCAHTOA, this is tangent. So we take the tangent of 20 degrees, the angle, equals opposite, which is 3.5, over adjacent, which is A, the apothem. Now we solve for A. Multiply both sides by A. These A's divide out, and we get A times the tangent of 20 degrees equals 3.5. Then to solve for A, we divide both sides by the tangent of 20 degrees. The tangent 20s divide out over here, and we get A equals 3.5 over the tangent of 20 degrees. Now this is the exact value of the apothem, so we hold on to this. We'll be using it here. We now need to find the perimeter, P. For the perimeter, remember, is P equal N times S, where N is the number of sides in the polygon and S is the length of one side. According to our problem, P is equal to N, which is 9, times the side length, 7 centimeters. That gives us 63 centimeters for our perimeter. Now we use our perimeter, and we figure out our area. So we have A equals 1/2 times A, the apothem, 3.5, over the tangent of 20 degrees, times 63 centimeters. At this point, notice that 2 will not go into either one of these numbers evenly. So we multiply 1 times 3.5 times 63, and then all the numerators, and we get 220.5. The denominators, 2 times the tangent of 20 degrees times 1 is 2 times the tangent of 20 degrees. This right here is the actual exact area of this polygon. They asked us for the approximation rounded to the tenths. So be careful when you use your calculator here. 220.5 divided by, and then you need to use a set of parentheses, 2 times the tangent of 20 degrees in your calculator, close parentheses, and then enter. This will give you approximately 302.9 square centimeters. So there's a little over 300 square centimeters inside the surface of that nonagon. Example 3. What is the area of a regular pentagon with 8-inch sides rounded to the nearest tenth? Pause the video and see if you can perform the operations on this to solve the problem yourself, and then turn it back on when you're ready. Okay, example 3, we're trying to find the area of this regular pentagon, where N then is 5. And working this problem is exactly like the previous one in example 2. We draw radii, DQ, and EQ, and the apothem A. So So starting with radius QD, or DQ, and then radius EQ, you can draw other radii if you feel like you need to, here, there, and there. Find the central angle here. We take 360 degrees all the way around. Divide by n the number of sides or angles. That's 360 degrees divided by 5, the number of sides in a pentagon. Once we divide, we get 72 degrees. So the central angle here is 72 degrees. At this point, to draw the apothem, take your straight edge, come straight down, creating two right triangles. The apothem, of course, A, will bisect the side of the polygon. It also bisects the central angle. So, the angle created by A, the apothem, would be 72 degrees divided by 2, which gives us 36 degrees. So, this is 36 degrees. And this is 36 degrees. Now I'm going to pull out a right triangle, this one right here, and draw it down here. This is the apothem right here. The length of one side from the problem gave us was 8 inches. Therefore this length here is 4 inches, half as much. This is 36 degrees, and we can use trigonometric ratio to find the length of the apothem if we use the tangent, because this angle, the tangent of that angle, is the opposite over adjacent. We have the opposite is what we have, the adjacent is what we need. So the area is 1/2 AP for a regular polygon, apothem times perimeter, and to find A, we use the tangent of the angle 36 degrees equals the opposite side over the adjacent side. That's 4 inches over A. Set up your equation, then solve for A. Start solving for A by multiplying both sides by A. These A's divide out, and we get A tangent 36 degrees equals 4. Then to solve for A multiplied with the tangent of 36, we divide by the tangent of 36 degrees on both sides. The tangent 36 degrees divide out over here, and we get the apothem is exactly 4 over the tangent of 36 degrees centimeters. So we'll be using this. Then for the perimeter, P is equal to the NS, the number of sides times the length of a side. So the perimeter is the number of sides, which is 5, pentagon, times S, which is the length of one side, which was 8 inches. That gives us our perimeter of 40 inches. We use this in our formula. So the area is equal to 1/2 times A, which is 4 over the tangent of 36 degrees, times P, which is 40, or 40 inches. This time we can divide out 2 with either the 4 or the 40. I'm going to use the 4. 2 goes into 2 once, 2 goes into 4 twice. Now we multiply the numerators. 1 times 2 times 40 is 80 over the denominators multiplying together. 1 times tangent 36 times 1 is the tangent of 36 degrees. This would be the exact, in square inches, this would be the exact area. To approximate, be careful to make sure that you put a set of parentheses around the denominator. So 80 divided by open parentheses tangents of 36, close parentheses, we get about 110.1 square inches. So about 110 square inches, the area of that pentagon. Example 4. A stop sign is a regular polygon or regular octagon. The standard size has a 16.2 inch radius. And so the radius of the stop sign blown up here is 16.2 inches. What is the area of the stop sign to the nearest square inch? They're asking us to find our answer to the nearest full square inch. That's the ones place, so be careful with that. So we have our stop sign is a regular octagon, as it's stated in the problem, so n is equal to 8. Now, this will be the first time we'll have a problem where we actually end up having to use a trig ratio twice, so make room. We're going to start off the same way we did before. Draw adjacent, an adjacent, radius, and apothem. Call it A. So here's our radius they've already drawn for us. Let's draw another radius here. You could come over here if you wanted to also. I'm just going to stay consistent with the other examples. There's another radius, it's 16.2, and then we draw an apothem. Before I draw the apothem, let's go ahead and find the central angle here first. So for the central angle measure, again we take 360 degrees and divide by the number of sides or angles. That's 360 degrees divided by 8 octagon. That gives us 45 degrees. So this is 45 degrees. Every central angle is 45 degrees. Then we draw an apothem. And recall the apothem A bisects the side. The side we don't know yet. So when we find it, we have to make sure that whatever we find for a piece of this will be doubled. And so let's go ahead and find one of these angles here. To do that, like before, we take the central angle, which is 45 degrees, and divide that by 2, since it's cut into 2 equal parts here and here. When we divide, we get 22.5 degrees. So, drawing one of these triangles, come out here. I'm going to make mine a little bigger. We can see a little better. Here's the apothem A, right here. Here's the radius, 16.2, here. And this angle right here now is 22.5 degrees. This one right here. Well, this time, we've been using tangent. This time we won't be using tangent. We've got the hypotenuse this time. We've got the adjacent and the hypotenuse. Adjacent, hypotenuse, that's so toa, so it's cosine. So the next thing we can do is get our formula ready. That's A equal 1/2 times the apothem times the perimeter to find the area when we're ready after we find A and P. So starting with the apothem, we have cosine of the angle, 22.5 degrees, equals adjacent, which is A, over hypotenuse, which is 16.2. So we set up our equation and we solve for A. This time we're going to multiply by 16.2 on both sides. The 16.2's over here divide out, and A is equal to 16.2 times the cosine of 22.5 degrees. So we have our apothem now when we're ready to use it over in our formula. Next, we need to find P, the perimeter, and P is the number of sides times the length of a side in S. So P is equal to the number of sides, which is 8, and then the length of a side we need to calculate or find using trigonometry. This time we use the same angle again, 22.5, except this time we need the opposite side. I'm going to call that X, but we need 2X. We need twice as long, so let's remember that we're going to find 2X. This is x, so using the sine, this would be the sine of 22.5 degrees equals opposite, which is x, over the hypotenuse. The number we do have is 16.2. So we set up this equation and we solve for x this time. Well, I need to multiply both sides by 16.2. When we do that, those divide out, and x is equal to 16.2 times the sine of 22.5 degrees. Recall that we said that we needed 2x for the entire side, so 2x is the length of a side S. So when we plug in our S, it's got to be twice as much. So we take 2x instead of x, so we multiply this by 2. And we multiply the 2 and the 16.2. Remember, do not touch the 22.5. Multiply it, divide it, add it, subtract it. You can't do that. So 2 times 16.2, 2x is the length of a side, S, as we defined it, and that gives us 32.4 sine 22.5 degrees. So here's our S. We take our S, we plug it in here. The perimeter is 8n, the number of sides, times the length of a side is this right here. 32.4 times the sine of 22.5 degrees. And this is in inches. We can still multiply the 8 with the 32.5, so we do that now. For our P, we get the P as simplified as possible. So that would be 8 times 32.4 is 259.2 times the sine of 22.5 degrees. Inches. There's our P. Now we can plug that in here also. I'm going to come down here. So A is equal to 1/2 times A right here, which is 16.2 times the cosine of 22.5 degrees times P, which we found to be 259.2 sine 22.5 degrees. At this point, remember these are both whole values, and so these are like, if you created fractions, it would be like this. The 2 doesn't necessarily go into either one of these numbers because they're decimals, although they will go into them because they end with an even number. So what we can do is multiply the numerators together. 16.2 times the cosine of 22.5 times 259.2 times the sine of 22.5 times 1 gives us 4,199.04 cosine 22.5 degrees sine 22.5 degrees. Notice we took these multipliers and multiplied them together over 2. 2 times 1 times 1. At this point, we divide this number right here by 2, and we can get a slightly more simple answer. That would be 2,099.52 cosine 22.5 degrees times the sine of 22.5 degrees. This would be our exact answer in square inches. We need an approximation, so we approximate now. Be careful in your calculator, make sure you're in degree mode. 2099.52 times the cosine of 22.5 degrees, close parentheses, times the sine of 22.5 degrees, close parentheses, enter, and you should get rounded to the nearest square inch. The ones place is 742 square inches. So the stop sign surface contains about 742 square inches. This is an actual stop sign for most city stop signs. Example 5. Graph each given linear equation on the coordinate plane. And they give us L1, L2, and L3 with these linear equations. Identify the type of polygon produced. Then, using a dashed line, graph one of the altitudes of the figure, or height of the figure, using the linear equation h right here, y equals 3x plus 2. Find the simplified exact area of the polygon. Okay, well, first of all, it's been a long time since we've graphed linear equations, so let's take our first L1, y equal x plus 4. Remember, in the form y equal mx plus b, the slope is the coefficient of 1, or x, which is 1. So the slope in this particular line is 1, or is rise over run, 1 over run. 1 over run. Rise over run. The y-intercept is b, where it crosses the y-axis, and so b is 4. So we graph that. We start with the y-intercept starting at 0, 0. We go up 4, positive 4. 1, 2, 3, 4. Here's one of our points in this line. And then starting from the y-intercept, we use the slope as rise over run. It's positive 1 over positive 1, so we go up 1, rise, run 1, to the right 1. We can do that several times, up 1 to the right 1, up 1 to the right 1. And to make sure that our line is straight on the graph, take your straight edge and draw. Make sure it goes through the correct points all the way through the graph. Completely clear both sides of the graph. There's our line 1. Now for line 2, we have y equal negative 2x plus 7, where the slope is negative 2, or as rise over run, negative 2 over 1, or 2 over negative 1. I'm just going to use this one. And the y-intercept is 7. So starting with the y-intercept for line 2, we start at the origin, we go up 7. 1, 2, 3, 4, 5, 6, 7. There's one of our points. Starting from the y-intercept, we use the slope of negative 2 over 1, just the rise over the run. So if the rise is negative 2, we go down 2, keep our pencil there, go to the right 1, since that's positive 1. So we end up right here. We do that several times, down 2 to the right 1, down 2 to the right 1, maybe one more, down 2 to the right 1. Take your straight edge, make sure it lines up all the way through the graph on each point of intersection there. And we get another line like this. Clear both sides of the graph. And this is line 2. Now it looks like we're having something starting to form. We've got this area up here, to the right, to the left, and down here. So let's see what happens when we do line 3. Line 3 is at y equal negative 1/3 x minus 4/3. This one will be a little harder to graph because our y-intercept is not a whole number. But you're going to see how it matches up pretty well with these other two lines. So the slope here is negative 1/3, or 1 over negative 3, either way. And then our y-intercept, of course, is negative 4/3. That means each square here cut up into 3 equal parts. We go 4 of them in a negative direction. So starting at the origin, to find negative 4/3, we're going to go down. We go 4/3. That's 1/3, 2/3, 3/3, which is negative 1, and then one more third. Cut this into 3 equal parts and go one of them. So this is 1, 2, 3, 4/3, right about there. Then we take our slope. We need to go down 1 and to the right 3. Well, be careful, because when we go down 1 full unit, it has to come down 1 full unit below this grid line. So there's 1, and then 3 to the right. 1, 2, 3. So right about there. Take your straight edge and notice that these line up real nicely with the 2 points of intersection here in the line 2 and here in line 1. Go ahead and Draw that line, clear both sides of the graph, and this is line 3. The polygon produced here is a triangle. So we've answered that question. Now they want us to find the area of this, but they first give us the equation, the linear equation for the height that they want us to use. This will also indicate which side we're going to use for our base. Because remember, height and base must be perpendicular. That's right. So they want us to graph h, which is at y equals 3x plus 2, where the slope is 3, or 3 over 1, rise over run, and b is 2. So we start at the origin, we go up 2. There's one of our points. Our slope is 3 over 1, rise 3, run 1. So I go up 3, to the right 1. And so it's this point right here. So we take our straight edge and very carefully line those two up. And I'm going to use the dashed line. We're used to seeing heights dashed or an altitude dashed. So which line which side of the triangle is going to be our base? The one that line 3 contains, this one right here, because it's perpendicular to it. And notice the slope is the negative reciprocal of this slope of line 3. And that makes sense. These make these perpendicular. Now we have to find the area. To find the area, we're of course going to use the formula for the area of a triangle, 1/2 base times height, where base and height are perpendicular. But we do need to find the length of the base and the length of the height. Therefore, we're going to need the ordered pairs for the endpoints of the base and the endpoints for the height, segment of the height. So here, this point is -4, 0. The point right up here is 1, 5. The point over here is 5, -3. Then we'll need this as an endpoint to find this length. So this is at -1, -1. So we're going to find the length of this using the distance formula and find the length of the height using the distance formula. So starting with the base, we have the square root of. Remember, we're going to use these two ordered pairs for the base. Starting with x2, we have 5 minus -4 quantity squared plus, and then back over here, -3 minus 0 squared. So the base is the square root of 5 minus -4 is 5 plus 4 squared plus -3 minus 0 is -3 squared. This gives us the square root of 5 plus 4 is 9 squared plus -3 squared. And this gives us the square root of 9 squared is 81 plus -3 squared is 9. This gives us the square root of 90. We must simplify this. The square root of 90 factors, there's a perfect square factor of 9, 9 times 10. And so b is at 3 root 10. So we'll be using that for our base. Now for our height, the square root of, using the distance formula, with these two endpoints. I'm going to go ahead and start with my second endpoint, -1 here. -1 minus +1 quantity squared plus, then going back over here we have -1 minus +5 squared. So our height is the square root of -1 minus 1 is -2 squared. Don't forget your parentheses. -1 minus 5 is -6 squared. So the height is the square root of -2 squared is 4 plus -6 squared is 36. And this gives us 36 plus 4 is the square root of 40. Square root of 40 must be simplified. So we take that and factor out a perfect square factor, 4 times 10. And so h is, the height is 2 times the square root of 10. Now we can find our area using our formula here. So the area is 1/2 times the base, which is 3 root 10, times the height, which is 2 root 10. So then we have 1/2. These three factors, the 2 here and the 2 here, are both rational, so we can divide those out. 2 goes into 2 once, 2 goes into 2 once, and now we have 1 times 3 root 10 times root 10. So we have 3 root 10 times just 1 root 10, or root 10. This is 3 times the square root of 10 times the square root of 10 is the square root of 100. Square root of 100 is 10, and so we get 30, exactly 30 square units for this, the area of this triangle right here.